The first problem in the final exam is going to be a first order circuit. And in this particular example, it asks us, given the circuit, relatively complex circuit on the left, to find I sub C, the current through the capacitor for all time. And then secondly, to plot that current through the capacitor for 5 time periods. So let's begin. First step in analyzing this is to ask, what method are we going to use? You know, since it's problem 1, I've already told you we're going to use first order circuits. But if I didn't tell you that, you take a look at it and you'd say there's only one, there is an energy storage element, and it's this capacitor right over here. So we know there's going to be some time varying component to it, but we only have one capacitor. And then the next question is, are we powering it from switched DC sources, or are we powering it from a sinusoid, in which case we'd want to use phasor analysis methods? Well, here you can see it's definitely, we're powering it from switched DC. So we're going to use the first order circuit analysis method. So to analyze the circuit, we're going to begin with 5 steps like we always do. And the first step is to draw the circuit for time less than 0. And our goal is going to be to find what that voltage is across that capacitor. Now, the question asks, what is the current through the capacitor? But for first order analysis, we don't care what the question asks. We always find what the voltage is across the capacitor, if it's a first order circuit with the capacitor, or what the current is through the inductor, if it's a first order circuit with an inductor. So since this has a capacitor, we want to find the voltage across the capacitor. We draw it for time less than 0. We see there's a switch. We know that we're not going to draw any switches, and we're not going to draw any capacitors or inductors in this circuit. We're also not going to draw any U of T's. This circuit just has a switch and a capacitor. So let's see what that switch does. When you see a switch and it has an arrow, what I want you to think of is that this switch is on a fulcrum point that's pivoting down here, and it moves in the direction of the arrow at time equals 0. So that means before time was 0, it looked like this, and then for time greater than 0, it had to look like this. And we've got these other 2 contact points here. So here are those 2 contact points. So for time less than 0, it contacted this point, and for time greater than 0, it contacts that point. All right, so given that, we see it swings from left to right at time equals 0. So for time less than 0, it had to swing, it had to be in this left position. So we can think of it, just for the purposes of drawing this circuit, that it looks like this for time less than 0. Now, this wire looks kind of suspicious. It can't have any current going through this wire, because if we draw a node around it, the rule KCL says that the sum of all the currents exiting that node has to be 0. Well, there's only one wire exiting it, so by definition, that has to be 0. And if it contributes no current at all to our circuit that we're interested in, we don't need to draw it. We can actually see that there's more stuff that we don't need to draw. If we were to graph this node around here, we can see that the only wire that this intersects, that this node hits, is right here. And so therefore this wire carries no current. And since it carries no current, it doesn't affect the thing we're interested in, which is the voltage across the capacitor. Now, if we were asked to find the voltage someplace here, of course, we can't ignore drawing this, because this encloses the part that we're asked to find. But in this particular problem, we need to find the voltage across the capacitor. This is outside that part, so we don't need to draw it. So now we can simplify our circuit tremendously. And it's saying it's just a 2-volt source with a 9 ohm and our capacitor. And then recall that for DC steady state, which this is, capacitors look like opens and inductors look like shorts. But the next question is, where do we draw this VC naught? Do we draw it with a plus at the top or the bottom, or does it matter? And the answer, it matters a whole lot. This is a passive component. If we call the current going down for any passive component, we have to define the voltage as being more positive entering and more negative exiting. So therefore, we have to define that voltage across that capacitor in that way. Just so we don't get confused later on, I'm going to redraw our switch correctly. Whoops. With the fulcrum down here and with an arrow that shows that it's moving left to right at time equals 0. And now for time less than 0, it all boils down to this. And just by inspection, we see that the voltage source on the left guarantees that this node over here, everywhere on this node, is 2 volts higher on the top than everywhere on the node on the bottom. And so by inspection, we have our VC naught being 2 volts. And that's the first step. Second step, we have to draw the circuit for time greater than 0, and our goal is to find tau. It's always important to know what you're looking for. If you don't know what you're looking for, you might simplify away the wrong part. So for time greater than 0, now this switch is on the right side. And now using the same reasoning as we did before, there can't be any current flowing through this 2-volt source, so we don't have to draw it. But unfortunately, we do need to draw the rest of the circuit, which is much more complicated. So we've got this 18K up on top. We've got a 9K beneath it. We can see that this switch is to the right. So we've got another 9, and it looks like I misdrew this. We should have had K's over here. This won't affect the analysis. And now we've got this capacitor over here. We want to find tau. This capacitor has a value of 5, 6 millifarads. So to find the tau, what we need to do is to find the resistance that that capacitor sees. And to do that, we're going to set all of our voltage sources to 0, which makes them shorts, all of our current sources, if we had them, to 0, which makes them opens, and we'll redraw our circuit from the capacitor's perspective. So when I make this 0, I'm just going to move these 2 resistors over sideways. So we have an 18K, and we have our 9K, and we have our other 9K, and we have our 5/6 capacitance, millifarad capacitance. We want to find what the REQ is that that capacitor sees. So there's several ways to do this. The not very smart way to do this is to say REQ is equal to 1 over 18K plus 1 over 9K plus 1 over 9K. Grab the calculator and hope you don't make a mistake. There's nothing mathematically wrong with that, but it's not the fastest. One way that I think you could be a little bit faster is to say, hey, these 2 9Ks are in parallel. And I know that whenever I've got 2 things in parallel, it's equal to 1/2 their overall resistance. So I could say this is like an 18K in parallel with a 4.5K. And now I can figure out the resulting thing by saying it's product over sums. 18 times 4.5K. I'm just going to get rid of the K's. It'll work out the same either way. Over 18 plus 4.5, and that whole thing is in K. So this is method 1. This is the slowest and most prone to error, because people have trouble with these 1 overs when they put them in their calculator. This is method 2. This is smarter, still not the smartest. The smartest way is to go back to this thing and realize that all these guys are multiples of each other. There's a 9K, there's a 9K, there's an 18K. Since this is multiples of each other, we can recreate this with the largest value resistor. And watch how we can do this. Here's our 18K. That 9K we could create by putting 2 18Ks in parallel. These 2 18Ks is this 9K. This 9K we could create by these 2 18Ks. And so with no math at all, you can say that the whole thing is just 5 18Ks in parallel. So it's just 18 over 5K, and that's our REQ. And if you didn't follow all that, it's okay. Go back to one of the other methods that involves the calculator. But after a while, you can just look at this and do this in your head and just look at it and say it's equal to 18 over 5K. So now we can finally answer our overall question, which is what is our tau? For a capacitive circuit, it's RC. If it was a inductive circuit, it would be L over R. But since it is resistive, it's going to be our REQ is 18K over 5. And our capacitor, we said, was 5 over 6 milli. So the 5's cancel, and we get 18 over 6. The K times the milli cancel, so we just get 18 over 6, which is equal to 3, and the units would be seconds. Let's move on to the next. Next step is to draw it at time equals infinity, and the goal is to find our VC of infinity. So when we draw it at time equals infinity, this is still over on the right. It looks a lot like this, except we have no switches, which we don't have here. We have no capacitors though. So our capacitor, DC steady state, it looks like an open. So now we've got our 10-volt source. And we've got our 18K and our 9K. Why don't we just simplify that right now? You can either do 18K, 9K using this rule or using product over sums, but I'm going to do this thing. I can do it in my head. This 9K looks like two 18Ks in parallel. We've got three 18Ks in parallel, three of the same valued resistors. It's just equal to 1/3 then of 18K. So just in our heads, we can simplify it down to 6K. I hope I've convinced you by now how useful that method is. And our capacitor, once again, since we're in DC steady state out at time equals infinity, looks like an open circuit. And so here's our VC of infinity. So you can see this is just a voltage divider. The only place that current flows is around in this circle. And so it's going to be equal to our input voltage times the voltage across which we're interested in, times the sum of all of them. So the K's cancel and we get 9 over 15. And let's see, we can divide through this by 5. So we get 2 times 9 over 3. And then we can say that's equal to 18 over 3 or 6 volts. Now, the third step is to plug it into our plug and chug equation. And that is the voltage across the capacitor at time t is equal to V of infinity plus V naught minus V of infinity all times e to the minus t over tau. So our V of infinity is 6. V naught is 2 minus 6. That gives us minus 4 e to the minus t over our tau, which we said is 3. That's our simplest step. Of course, this is only valid in certain regions. This is only valid for time greater than 0. For time less than 0, we already found it in step 1. Step 5 is to go back to what we were originally asked to find, which is IC. Let's figure out how we can find IC given our VC. So let's see, for time greater than 0, what's the relationship between the current through this and the voltage across it? Well, if it was a resistor, we could use Ohm's law. Since it's not a resistor, but it's a capacitor, we can use the constitutive relationship for a capacitor and say the current through it is equal to the derivative of the voltage across it. So what we need to do is take the derivative of this and multiply it by C. Our C we said was 5 over 6 millis. And the derivative of this is pretty easy. The derivative of a constant goes away. The derivative of the rest of it, this minus cancels with this minus, and we get 1/3 times 4 e to the minus t over 3. So let's see, that gives us 5 times 4 is 20 over 6 times 3 is 18 e to the minus t over 3. Now this milli comes out and it just becomes milliamps. And we're almost done. We can simplify this a little bit to 10/9 e to the minus t over 3 milliamps. So that is what our current is for the region time greater than 0. Unfortunately, it asked us to find it for all time. So we're going to have to go one step more complicated than that and say this is what it is for time greater than 0, but we need to analyze it for what it is for time less than 0. Well, we already drew exactly what it looks like for time less than 0 over here. And for time less than 0, you can see the current through this open is going to have to be 0. So for all time, this is equal to 0 amps for time less than 0, or 10 over 9 e to the minus t over 3 milliamps for time greater than 0. And what is it at time equals 0 exactly? We really don't care because there's no energy associated with what it is at that exact moment in time. If you want to get extra cool points, this is a 100% correct right answer. If you want to get extra cool points, you could say it's equal to 10 over 9 e to the minus t over 3 times u of t milliamps. And now in one equation, you've gotten everything. Since for time less than 0, you're multiplying this by 0, so you get your 0. That's more advanced. If you didn't get that, doesn't matter. 100% either way, that's our answer for part A. For part B, it just asks you to graph it. So let's plot it quickly. Here's our time. Now, it's 3 seconds for every time period. So 5 time periods will give us 1, 2, 3, 4, 5. You know, after 5 time periods, your final answer will be within 1% of its final value. To see that, after 5 time periods, you'll always get something that looks like e to the minus 5, right? Because you've got this t over tau. So when t equals 5 taus, the taus cancel and you get e to the negative 5. And that's really close to 0.01. And you don't need to work this out all the time. You just need to remember that 5 time periods, you'll get within 1% of your final value. And so that's pretty darn close to 0. So now we can plot what this thing looks like. And we can say it starts off at 10 over 9 millis, and it evens out so that after 5 time constants, which is 15 seconds, it's pretty close to 0. Maybe a better drawing would show a little bit more of a curve in it like this. And that's it. That's the final result.